So we were in the middle of looking at the simplest case of gravitational collapse, and we had a situation more or less as follows. We've got a collapsing body here. Inside was a region of constant density. And we had let the thing start to collapse under its own gravitation, so that if we drew a sort of picture of what was happening as a function of time, it looked something like this. And what we had done was said that outside the collapsing body, the metric was exactly that of the Schwarzschild solution. And we discovered the equation of motion for a particle sitting on the surface of this collapsing sphere. So we're going from here to here to here. And we've done that by solving the geodesic equation for that particle. And it told us the following results. In terms of where it is in space, r as a function of eta was equal to big R into 1 plus cos of eta, and the proper time as a function of eta for that particle was equal to r cubed over 8m to the 1/2 into eta plus sine eta. So the thing started off at rest, and then underwent gravitational collapse, reaching essentially what looks like a point here after an interval eta equals pi by 2. I beg your pardon, e equals pi, not pi by 2. So that's fine. That tells us what happens outside the collapsing body. But what we would now want to do is to find out what the metric inside the collapsing body is. Let's have the end point here. In actual fact, you all know the answer to this question. The answer to this question is best found by staring at this relationship here and asking whether you recognize it. Even Cambridge students have something to say when asked this question. Does this look like something you have seen before? Cambridge students are known to be very quiet. Oh, yeah, that's pretty good. Yes, the answer is yes. If you look at a k equals 1 FRW model with pressure-free matter, then its size looks almost exactly like this. In fact, if you write the metric in the following form, minus d tau squared plus a squared of tau into d chi squared plus sine squared chi d omega 2 squared, you will be able to write down how a of tau behaves, and you will discover that a of eta hat is equal to some a max into 1 plus cos of eta, t of eta hat I should have an eta on it, is equal to half of A max into eta hat plus sine eta when we look in the collapsing phase. So that's a hint that we should be able to figure out what the metric is inside this region. On the surface of this thing, you know that a particle is essentially doing the same thing, because these are the same things as these things. And so what you can do is you can patch in part of this space-time into the interior of this collapsing body. To do that, you'd have to require that the assumption that the density remains constant in space, but that's precisely what happens here. And since solutions of the Einstein equations are unique, given the initial conditions under many circumstances at any rate, then we can guarantee that we found the correct solution. So what should we do? To make everything match up properly, well, of course, I can't draw this thing because this thing is a three-sphere, but I can draw it in one dimension down. So here is an S2. The analog of the angle chi is the angle from the pole. And all you do is you cut out a little bit of it here. Let's call this angle here chi max. Let's call it chi 0. And that tells you that this region here corresponds to this region of space-time for chi less than chi 0. So all you have to do is to match these two together, and to do that you just simply observe that capital R, that's the value of the radius when you start the expansion, has got to be equal to AM times chi 0. And sine chi 0, well, that's really all you need. And the total mass is equal to a half AM sine cubed chi 0. You get this relationship by matching up the densities, and remember that the density inside a Friedmann-Robertson-Walker model of this type is given by 3 over 8 pi A max 1 over A cubed. So you can see that 4/3 pi rho A cubed basically gives you the total mass of the thing. You can rewrite that in a slightly different way. AM, if you want to rewrite it, is equal to R cubed over 2m to the half, and sine chi 0 is equal to 2m over r to the 1/2. So what you've discovered is that inside this collapsing body, you just have this sort of cap part of a Friedmann-Robertson-Walker universe with k equals 1, which represents the collapsing body. So inside, outside you've got Schwarzschild, and inside you'd have FRW k equals 1, or at least part of. And of course you know that as eta goes to pi here, you end up with a singularity, which in terms of a cosmological model would be the big crunch singularity. So you can just simply record that fact. Eta equals pi gives a singularity. But now remember, it's a singularity that you find in a collapsing universe. So that's a simple example of gravitational collapse to find something singular. It's generic in the following sense, that if you change the equation of state, then you wouldn't change much of the general overall picture, but you would, of course, change the details of the metric. You can draw a Penrose diagram for this situation. And what you'll discover is the following. Outside the collapsing body, everything looks rather nice. The curvature is 0, well, falls off like 1 over r cubed, out giving you a well-defined infinity. There is, however, the collapsing body, which is going to look something like this. And inside the collapsing body, the metric is that of the FRW universe. It collapses to form a singularity, which we can write there, and there is a horizon which forms corresponding to just simply where r is equal to 2m. This thing is a singularity. So the picture is really very beautiful. It just simply says if you take a perfectly regular space-time and you initiate collapse here, then you will collapse to form a singularity, you'll collapse to form a horizon. There's no business about strangeness in the past, there are no singularities in the past, there are no past horizons. You simply have a nice situation in which a black hole forms, and that's the end of it. As I said, the picture is completely generic. You might easily think that such a simple picture was an artifact of having assumed spherical symmetry. That turns out to be untrue. Even from basic reasoning along the lines projected by Michel and Laplace so many years ago, you can be fairly convinced that a horizon will form when matter gets within its own Schwarzschild radius. That's sometimes called the hoop conjecture. It has been proved under a wide range of circumstances, but not absolutely universally. The conjecture was made by Thorne, I guess back in the 1960s. There is a proof, more or less a complete proof, by Yau. It basically says when a body gets within its Schwarzschild radius, a trapped surface forms. A trapped surface is the surface from which you cannot escape. We'll see a little bit later the difference between a trapped surface and an event horizon, but for static spacetimes and stationary spacetimes they are the same thing. So a trapped surface just simply means that you can't escape. So one way of thinking about a trapped surface is simply that it's where the Schwarzschild radius comes into play. It's just simply where light cones are always directed inwards. So this coincides with the idea of an event horizon for a situation that is stationary. Let me remind you that the horizon is the boundary of the causal past of scri plus. A proof of this theorem is beyond the scope of these lectures, unfortunately. It would take quite a long time to prove it. There is a second theorem which is of huge importance in the understanding of gravitational collapse, and that's the singularity theorem of Penrose. Let me make a qualitative statement of what this theorem says. It says, assume that the energy density of matter is positive. And there is a horizon. Then there must be a singularity in the space-time. Again, the proof of that theorem is rather hard and beyond the scope of these lectures, but a moderately readable account of it can be found in Hawking and Ellis, The Large-Scale Structure of Space-Time. There you'll find a moderately readable account of how this theorem actually works. But given those two results, it tells us that the gravitational collapse of something to form a horizon and a singularity is a generic state of affairs. And we can assume, for almost all purposes, that if gravitational collapse occurs, you will find a black hole which has a horizon and some kind of singularity. So at this point it would be nice to actually understand a little bit more the difference between a trapped surface and an event horizon. So without doing anything terribly complicated, we can easily do that. Let's look at what happens if you try to form a black hole and you think you know what's going on. So you could have some collapsing matter here. This picture has some defects, which is that it doesn't make the singularity look space-like. But suppose you had a collapsing body to form a singularity that looked something like this, and here was what you thought the event horizon was. We'll call this a trapped surface, where the black hole has settled down to some kind of equilibrium state. If that's all there was to it, this trapped surface would be the event horizon. However, let's change the rule of the game slightly and imagine that 1 billion light years away, somewhere out here, there was a very dense shell of matter which was also undergoing gravitational collapse. Something like this. It doesn't really matter where it is, it just has to be a long way away from the black hole. It could be that at some point it gets within its own Schwarzschild radius, let's say here. Then from there onwards the green surface is a trapped surface, and before that it isn't a trapped surface. So let's change the colour there so that we actually see the difference. What does that mean for the event horizon? Well, the event horizon is obviously here, but what happens to an observer sitting, say, here? An observer sitting here cannot escape to infinity. Let's suppose that they move outwards at the speed of light. They will get to here, and then they'll get stuck. So obviously this point here is inside an event horizon. What is the last point from which an observer can escape to infinity? Well, the answer is it's going to be some line here, where this is basically the same as the speed of light, moving out from here. So in actual fact, let's not continue that out there. Anyone in this region here, cannot escape to infinity. So this corresponds to the event horizon. This green surface is a trapped surface because you can't escape from it. But if you're anywhere in the middle or inside the black hole here, then of course you can't escape to infinity. And that illustrates the difference between an event horizon and a trapped surface. The event horizon, you need to know about all of the space-time. You can't, by any local observation or calculation, determine where the event horizon is. But you can determine where a trapped surface is. A trapped surface corresponds to a surface where the rays of light are not expanding. Whereas an event horizon is something which you only know once you have found all the trapped surfaces. an event horizon, you need to know everything. So these things are not the same. So that's what happens in gravitational collapse. And it's a nice, coherent picture. If you're interested in astronomy, then lots of people simulate gravitational collapse. But it's something which is really has become a numerical art rather than anything else. So let's now move back to black holes, and in particular black holes that are basically have reached their final state. So you want to think about what I'm going to say in terms of the Kerr-Newman family of solutions, where things have settled down. So whether things have reached equilibrium after gravitational collapse. Just by staring at the metric, we knew that it was stationary and axisymmetric. The nice coordinate way, invariant way of telling that those are the cases is that there is a killing vector TA, which represents time translations. And it's normalized such that TA d by dxa is the same as Minkowski time coordinate at infinity. As spacetimes are also axisymmetric, that means that there is a rotational killing vector such that Ra d by dxa is d by d phi, again in the set of coordinates that we were using before, where as r went to infinity, t r theta phi coordinates looked basically like Minkowski space. These were the two killing vectors that we found, which generated the isometry group R cross U1. T was defined to be time-like outside the ergo region. So the question is, what killing vector, if any killing vector, is going to be null on the horizon? Whatever it is, this killing vector has got to be a killing vector because the horizon is stationary. It doesn't evolve in time. So it must correspond to a killing vector. Simply because light rays moving up the horizon don't do anything. That is to say that there must be a killing vector which is tangent to the horizon. So, since there are only two killing vectors involved, it must be some linear combination of these two, and we'll call this object Ka. If we want this thing to be null on the horizon, that defines this quantity here, omega. Another way of writing this would be to say that Ka d by dxa is equal to d by dt plus omega d by d phi, and so you can see that omega basically behaves like an angular velocity. Furthermore, if we say that k is going to be null on the horizon, then this angular velocity represents the angular velocity of the horizon as seen from infinity, because it is defined in terms of these coordinates t and phi. Well, let's draw a little picture of what's going on. So here is the horizon. Here is a light ray moving in the horizon. And if you took a section of constant time, which would be advanced time on the horizon, and compared it to the previous time, then nothing will have changed as you go from there to there. So that tells you that this surface is isometric to this surface, and it's a continuous transformation because the surface can be moved up anywhere, and so this direction must be killing. So what is the angular velocity? Well, it's fairly easy to calculate. If you want this thing to be null, I'm going to get rid of this. Recall that TA is 1, 0, 0, 0. RA is 0, 0, 0, 1 in the language where this thing is TR theta phi in that order. And so Ka equals 0 is the same thing as saying that Ta plus 2 omega Ta Ra plus omega squared Ra is equal to 0. But turning that into components of the metric, this thing is just GTT, because if you lower this t, all you get is a GTT, plus 2 omega GT phi, plus omega squared G phi phi. So it's a nasty quadratic equation to solve on H. Where is H? H we already know to be R is equal to m plus the square root of m squared minus a squared minus q squared. So you can work out what omega is. you will discover that an explicit calculation tells you that this is equal to a over 2m squared minus q squared plus 2m times the square root of m squared minus a squared minus q squared. It's kind of hard to find this in the literature. It's an unpleasant calculation to do, so it is important to write down this particular result and not forget it. When deriving this, of course, we assumed that object here, inside the square root, this thing was taken to be positive or 0. Otherwise, of course, you don't have a black hole. So here is this rotation, the angular velocity. You'll see it depends on the rotation parameter a in a linear fashion on top. If a is equal to 0, it's equal to 0. There is one thing that I really want to emphasize about this, and this shows explicitly that the thing does not depend on where you are on the surface of the black hole. It does not depend on whether you're at the North Pole, South Pole, or the equator. It's the same everywhere. So it's independent of the position on the horizon. You can put it another way if you like. You could say the black hole is rigidly rotating. In other words, it's rotating like the Earth does. The Earth does not rotate at different speeds at the poles and the equators. It rotates at the same angular velocity everywhere. However, that's unlike the Sun. The Sun has differential rotation, and it is rotating faster at the equator than it is at the poles. So, in that sense, it's more like a solid object than like a gaseous blob like a star. Again, notice that omega depends only on three constants: the mass, the rotation parameter A, and the electric charge on the hole. It doesn't depend on anything else, and so it really is a derived quantity once you have been told what the parameters of the black hole are. So the next question I want to ask is whether or not there are some similar quantities that you can define that are useful, and its precise use will be seen shortly, that are determined by the parameters of the black hole. The first one is just going to be the area of the event horizon. We already know that this is essentially a sphere with radius r given by m plus the square root of m squared minus a squared minus q squared. And so its geometric area, I'll just call A, is equal to 4 pi times this thing squared. Or if you prefer it, 2m squared plus 2m square root of m squared minus a squared minus q squared minus a squared minus q squared. You will notice that this combination here, 2m squared plus 2m squared times the square root of this thing minus a squared minus q squared, is the same thing that shows up here. But now I realize that something has gone slightly wrong. No, it's not. There really is a minus a squared, but there is no minus a squared here. The next quantity of importance is sometimes called the surface gravity of the black hole. This is defined in the following way. We know that k is a killing vector. We also know that it's parallel to the geodesics on the horizon, and therefore it should obey the geodesic equation. Well, that's fine. Let's write down the equation it obeys. One's first thought that it should obey an equation that looks like this. Probably equal to 0, but if you did that you'd be wrong. It's proportional to KB, and the constant of proportionality is usually called kappa. The reason that this term appears is that because we have written Ka in the form d by dt plus omega d by d phi, so that this thing is basically normalized to be time translations with respect to Minkowski time at infinity, there is no guarantee that this t is an affine parameter along the horizon. If you have a geodesic where t is not an affine parameter along the horizon, or in general dxa by dt defines the curve in question, and this is not an affine parameter, you will always end up with something proportional to the original tangent vector to the surface. So this thing is guaranteed to be there. It might be that kappa is equal to 0, but often it is not. Kappa is referred to as the surface gravity. It does have the dimensions of acceleration. In the units, excuse me for one moment. Well, whoever it is has gone. Gravity g is an acceleration, has dimensions of length over time squared. So if we go back to more sensible units, this thing has got dimensions of 1 over length, c being equal to 1. This thing has got dimensions of 1 over length, so it really does look like a gravity. It's an acceleration. And if you evaluate it, you will discover that kappa is equal to the square root of m squared minus a squared minus q squared divided by 2m squared minus q squared plus 2m times the square root of m squared minus a squared minus q squared, where this thing is the same as denominator in omega. Again, notice that this thing does not depend on where you are on the horizon. Also notice something else. M squared minus A squared minus Q squared is positive for what we called case A of the Reissner-Nordstrom and Kerr-Newman metrics, but it's equal to 0 for these degenerate cases where the inner and outer horizons had merged. So it could be that that happens, but in that case this thing really would be affinely parameterized. So that's something that one should pay attention to. Now, in practice, everybody has trouble computing kappa. Here, it looks like a simple task because all you have to do is to know what the killing vector is, and you're done. So it ought to be, in principle, very easy to calculate it for some black hole space-times. However, there's a catch. And the catch is something that really needs to be pointed out. It's just called surface gravity because it's always been called surface gravity. You want to know what it means physically? But wait and see. So let's ask ourselves how we would calculate kappa. I'm going to do it for the Schwarzschild metric. So the Schwarzschild metric, we would be inclined to draw a Penrose diagram that looks something like this. And so we know what the killing vector is. It's d by dt in tr theta phi coordinates. And you could try to calculate the killing vector kappa from that formula by plugging it into here. If you do this, you will fail. And the reason that you will fail is because if you think back to lines of constant t in this picture, lines of constant time look something like this. We're interested in the properties of the horizon up here on H+. The green lines do not go through H+. They only go through this sort of peculiar crossover point between the past and future horizons. And in the case of gravitational collapse, this surface simply doesn't exist, and this surface starts somewhere. So trying to do it in terms of tr theta phi coordinates is futile. What you have to do is to use a set of coordinates which are sensible on H+. Those would correspond to the Eddington-Finkelstein coordinates Vr theta phi. the metric in those coordinates is ds squared is equal to minus v of r dv squared plus 2 dv dr plus r squared d omega 2 squared, and v is a coordinate which goes up the horizon and looks something like this. V goes up in that direction. So let's do this calculation. Once you've done it once, you don't need to do it again, but it does involve one trick. So what is Ka under these circumstances? Ka d by dxa is equal to d by dv, time translation up the horizon. Explicitly, Ka in v r theta phi coordinates is equal to 1, 0, 0, 0. But we need to know what it is with the downstairs index as well. GAB, the metric tensor, is equal to minus v, 1, 1, 0, and some junk down there that we don't care about. The inverse metric, GAB with its indices upstairs, is 0, 1, 1, v, and some junk down there that we don't care about. And v is, of course, 1 minus 2m over r. Now we can just write out the geodesic equation. Ka del A Kb is the same thing as Ka partial dA Kb minus gamma ABC Kc is equal to kappa times Kb. Most of this will disappear. We're only interested in what this is on the horizon, so we want to evaluate this on h. Notice that v is equal to 0 on h. It's the fact that v is equal to 0 that will give you trouble unless you do things this way. So this becomes kv dv kb minus gamma c v b kc summed over c is kappa kv. Nothing depends on the advanced time coordinate v, so this term doesn't give you anything. This second term involves kc, so let's lower the metric, using the metric to find Ka with its indices downstairs. What you'll get is minus v 1, 0, 0. So you'll notice that this thing vanishes on the horizon. That thing tells you immediately that the v component of this equation is worthless, because you're going to get a 0 here, and that doesn't give you anything useful. So put b equal to r. Then you'll get kv, which is equal to 1, times minus gamma v. B is equal to r. There are two possibilities here, v and r. So we'll end up with that. Kv with its index downstairs is equal to 0. And so we discover that kappa is equal to minus gamma r v r. Now let's calculate gamma r v r. Gamma r v r is equal to a half g r anything minus d a anything g r v plus d r of g v a plus d v of g a r. The only possibilities for A are either R, but that vanishes, or V. So this thing is equal to half of GRV into minus dV of GVR plus dR of GVV plus dV of GVR. These are 0. This thing is just d by dr of V. GRV is equal to 1. So this thing becomes a half d by dr of V with a minus sign, because there's a minus sign in GVV. So this is equal to minus 1 half d by dr of 1 minus 2m over r, evaluated on the horizon, which is minus a half minus 2m, differentiate 1 over r, you get minus, so I get that, which is equal to m over 4m squared, which is equal to 1 over 4m, and there's a minus sign there and there. So we have discovered that for the Schwarzschild metric, kappa is equal to 1 over 4m. So that's nice. You can do the same for Reissner-Nordstrom fairly straightforwardly. To do the same for Kerr is a nightmare. Well, not a very bad nightmare, but bad enough. Yes. No. No. That will give you the Schwarzschild metric at infinity, but it will not give you the Schwarzschild metric if you ask yourself about the entirety of the space-time. So it will not give you Minkowski space if you look at the entirety of the space-time. That's because there's a discontinuity as you go to m equals 0. It's true that the metric in Schwarzschild coordinates as m goes to 0 gives you what you expect. But the global structure of the space-time is quite different. That doesn't look like Minkowski space. So however small m is going to be different. So there's a discontinuity that happens when m equals 0, which you don't see from just staring at the metric. That's an argument that tells you that you really have to consider all the extensions when the coordinates go bad. Now, what about the electromagnetic field? Well, the electromagnetic field is really no different to any other field. It's just simply some gauge field. But one way of defining charges, which is rather nice, is to use a flux integral. I just wrote down Q over R for A0 and said that that looked like a charge when you looked at infinity. But you can do better than that. So here is what you could do if you wanted to do better. Take FAB, the electromagnetic field strength tensor. It's equal to the partial dA of B, AB minus dB of AA. I can integrate this thing over a big sphere at infinity, appropriately normalized. And that should be the charge. If this needs any explanation, just think about what's happening in Minkowski space. So I'm just thinking about the TR plane. In Minkowski space, this is minus dt squared plus dr squared plus r squared d omega 2 squared. What is dsAB? This is the surface area element This is composed from the induced metric on the surface. I should have said this is at t equals constant as well. Times the two normal vectors antisymmetrized. So the AB is multiplied by a half TA NB minus TB NA, where these are the two orthogonal unit vectors to the surface in question. Let's try and draw a picture of that. Here is a surface that's enormous of t equals constant. I can construct a big circle of radius r. And ask myself, what are these unit vectors? Well, TA is just 1, 0, 0, 0. RA is 0, 1, 0, 0. So TARA is equal to 0. And so DSAB is going to be something like r squared sine theta d theta d phi if times a half if A is equal to t and B is equal to r, and minus a half r squared sine theta d theta d phi if A is equal to r t. So I can now evaluate this thing by doing the integral to infinity. FTR well, AT I said was Q over R squared. Sorry, Q over R. The other components vanished. So FTR is equal to minus dr of AT is equal to plus Q over R squared. I think actually with these sign conventions I need a minus. No, I don't. That's right. I got it right. So that tells you that Q is 1 over 4 pi integral Q over R squared sine theta d phi. So that works to give you the charge as an integral over the surface. Now let's expand this a little bit to deal with a more general situation. let's take our black hole space-time and do something similar. There's a big surface out at r equals infinity. And then there is going to be the horizon sitting here somewhere in the middle. I want to regard the horizon as a boundary of a region that I can actually observe. So let's ask ourselves what happens if we apply Gauss's theorem to this integral to give you the charge on a particular space-time. Q is equal to 1 over 4 pi, integral over the sphere at infinity, if we apply Gauss's theorem to this, we will get 1 over 4 pi, integral now over r equals r horizon, t equals constant, dsAB, FAB, plus 1 over 4 pi, integral dsAB, sorry, not dsAB, d sigma a dB FAB, where this is the surface that is lying between the two boundaries, so it's everything shaded in green here. So this is a surface of t equals constant, and so this d sigma a is the volume element on that surface from the induced metric on the surface times TA. But by Maxwell's equations, this last term is equal to 1 over 4 pi d sigma a times the electric current, JA. That index should be downstairs. So what that tells us is that for our black hole space-times, there is, of course, no current because it's just outside the black hole's just electromagnetic field. And so this tells you that the charge isn't really on the at infinity. The charge is really sitting on the horizon or somewhere interior to it. That's just from Gauss's theorem. We'll meet a bit more of Gauss's theorem later. There is another quantity that is derived from the properties of the black holes and their electromagnetic field, and that is the electric potential of the black hole. This is usually called capital phi, and it's equal to TA evaluated on the horizon. You should protest that there is, of course, an arbitrary constant involved here. The arbitrary constant has been chosen such that A goes to 0 at infinity. This is just the same thing as the usual electrostatic potential. So what is this quantity for the Kerr-Newman family of solutions? Well, again, it's easy to work out in principle, but not so easy in practice. You will get phi equals Q times some mess. The ms is m plus m squared minus a squared minus q squared all to the 1/2 divided by 2m squared plus 2m times the square root of m squared minus a squared minus q squared to the 1/2 minus a squared minus q squared. And that's electrostatic potential. Again, notice that this does not depend on where you are on the horizon. The horizon is an equipotential, which would tend to make you believe that the thing was a perfect conductor of electricity. For a comprehensive discussion of this, there are some papers of Blanford and Znaek, and it can result in interesting astrophysics of black holes. We're now in a position to make our first observation that has something to do with thermodynamics. We have a collection of derived quantities. Kappa, phi, and omega are all constant on the horizon. This is sometimes called the zeroth law of black hole mechanics. That is a good place to take a break. So 10 minutes and then back here. So we may as well start. For the electric charge we had a nice flux formula, and it's often asked why are there no similar flux formulae in general relativity. That of course presumes that there are no such similar formulae, but there are formulae which come in two different kinds, and in actual fact, I think for our purposes we should regard them as did this thing stop working? That's better. So maybe it's running out of electricity or something. Well, it seems to be working fine at the moment. Let's not worry about it till it gives up completely. So we can define a mass in the following way. We can just simply take a vector field. It really could be any vector field, but I'm going to take the time translation vector field, TA, and construct a flux integral exactly the same way that I did for charge. M is 1 over 4 pi integral dATB times dsAB. This is what's usually called a Komar formula. The fact that it's a Komar formula reflects the fact that T is a Killing vector. In actual fact, that's unnecessarily restrictive. Another way of viewing the same thing is that if you just use Noether's theorem, you can write down an identical looking formula for T being any vector field. So it's really a special case of a Noether charge. But it happens to be particularly simple to interpret if this thing is a Killing vector. So what would you get? Let's apply it to the circle r equals infinity, t equals constant. In this particular case, what do you get? You get what is usually called the mass parameter of the space-time, meaning the in the sense that G00 was equal to minus 1 plus 2m over r plus some higher order junk. So that's what you would get. But if you apply Gauss's theorem to this, what you will get is equal to, in a situation like this, where this is an event horizon of the black hole, 1 over pi times over r equals the horizon at t equals constant, dATB plus 1 over 4 pi integral dA TB d sigma b. So you discover that there is a term on the horizon, volume term. This thing really does seem to be not in the best shape. Looks good. Thank you. So what is box acting on a Killing vector? Well, del A of TB, well, a Killing vector obeys del A TB plus del B TA equals 0. So this thing is equal to minus del A del B TA. And if I commute these two derivatives, I will get minus R A B A C T C from the Ricci identity minus del B del A of TA. But del A of TA is 0 because you can contract the A with the B here and get nothing. I think I want to put a minus sign here to make this work properly. So let's substitute that in to this expression here. What are we going to get? We're going to get a slightly different formula now. It's going to be a mass that you find on the horizon minus 1 over 4 pi times integral of box T, which is the same thing as minus the Riemann tensor contracted on its first and third index, which is the same as the Ricci tensor. And here we have d sigma b, but that's perpendicular to, the surface is perpendicular to T, so I end up with it. So I can get rid of all of these minus signs. And then I will end up with, from the Einstein equations, a mass defined on the hole plus 2 times TBC minus half the trace of the energy momentum tensor times GBC TB TC. These T's define for us what we mean by the components of the energy momentum tensor. If we go back to the fluid form of the energy momentum tensor, that was P plus rho UA UB plus P times GAB. And so if you substitute into here, what you will get is MH plus 2 times this combination of stuff integrated over sigma, and you will end up with rho plus, when the dust settles, rho plus 3p integrated over sigma. So what that tells you is the mass that you measure at infinity, let's say the mass out here, let's call this M infinity. Is equal to the mass on the hole plus whatever energy momentum tensor that you've got around here. So this is essentially the relativistic energy density. It involves P as well as rho, which you know to be the general case in relativity. So in the absence of any matter, you can see that this tells you that the mass of the space-time, in the case of Kerr-Newman solutions, is essentially a mass which can be associated with the horizon. That was very specific to the case of a killing vector, but I want to emphasize that there are formulae like this for any vector field simply as a consequence of Noether's theorem. They may not all have such obvious physical meaning. So that is a justification for calling this thing the mass because it basically sums up the energy content of the space-time, or in this case just simply the source of the black hole. There is a precisely similar charge, J, angular momentum, that is associated with doing the same thing to the rotation killing vector. So just dA RB. The difference is, however, that in order to get the correct normalization, you need a factor of 1 over 8 pi there, not a factor of 1 over 4 pi. If you evaluate this last object for the Kerr-Newman metric, you will discover this is equal to A times M. And if you evaluate this for the Kerr-Newman metric, you will get M. So that's how you define a mass and an angular momentum for the black hole. It's simply physical quantities that they have associated with it. Now we're in a position to find what's usually called the first law of black hole mechanics. Suppose that I have a black hole that's sitting here. It's going to be described in equilibrium by the Kerr-Newman metric, and I'm going to throw something in. I don't know, your least favorite politician perhaps. And I find a new Kerr-Newman black hole. Let's suppose that the initial one had mass m, charge q, angular momentum j, and the final one had mass m plus dm, charge q plus dq, and angular dj, where this dj is parallel to that j. So this is an infinitesimal change, so whatever we throw in shouldn't be too big. We know that it's Kerr-Newman here and Kerr-Newman here. We know that the situation outside the black hole, except in this middle where there's a little bit of evolution going on, contains no matter. And so we can just simply ask ourselves, how does this things change as I go from one situation to the other? There is an incredibly complicated way of doing this due to Bardeen, Carter and Hawking, where they actually look at energy balance, but it's easier to use the fact that the Kerr-Newman family of solutions is unique, and therefore I can start off just by looking at the area of the event horizon A, which I know to be a function of j and m and q. And all I have to do is to differentiate this. So using the chain rule, dA is dA by dm at constant j and q times dm plus dA by dj at constant m and q dj plus dA by dq at constant j and m dq. I know what A is a function of j and m and q, so all I have to do is to figure out what these partial differentials are. This one is equal to 8 pi over kappa. This one here is equal to minus 8 pi omega over kappa. This one here is minus 8 pi phi divided by kappa. So I can rewrite that in a slightly more suggestive way. dm is equal to kappa dA over 8 pi plus phi dq plus omega dj. This is sometimes called the first law of black hole mechanics. It tells me how two neighboring states in equilibrium are related to each other. A physical interpretation of this is what was asked about a little bit earlier. dm is a change in the total energy of the system. Phi dq is the change in electrostatic energy of the system. This is the change in electrostatic energy for any system. Omega dj is the change in rotational energy of the system. Which leaves you wondering what kappa dA over 8 pi is. Well, there are two ways in which you can contemplate this. The first is, if you were a 18th century physicist, not a 19th century physicist, you would stare at this formula and say, oh, it's obvious, this is surface tension times a change in the area. In other words, it's the work you'd have to do to change the size of a soap bubble. The soap bubble would have surface tension kappa over 16 pi. However, if you were a 19th century physicist, you would regard this as nonsense, because you would say, surely this is the first law of thermodynamics, not the first law of black hole mechanics in some special situation, in which case from somewhere there's a TDS term. Where has that come from? Well, of course, you would like to associate dA with S and T with kappa, but you have no idea what the constant of proportionality is. That was first speculated on by Bekenstein back in 1970. His work was completely disregarded because everyone said, well, a black hole is black and therefore it has zero temperature, and therefore this can't possibly be true. Well, there things stood for a little bit. The next sort of place where there was progress is usually called the second law of black hole mechanics, which you can guess what it is. basically says that under certain circumstances, similar to the ones we have just outlined, the area of the event horizon must increase. So let's investigate that. The way to do this is a little bit involved. I make no apologies for that. It's like many computations in relativity. It's a little bit lengthy, but in this particular case, it does show us something which is quite universal about gravitation. And on the way, we're almost in a position where we could prove the singularity theorems of Penrose. So what I want to do is to consider how light propagates in a general space-time. Well, whatever happens is going to obey Maxwell's equations in vacuum. Del A of FAB is equal to 0. F is, of course, the antisymmetrized derivative of A. And the way in which you proceed with this kind of thing is to pick a particular gauge. I'm going to choose the gauge del A AA equals 0. And the first thing I need to do is to look at the equation of motion that I get from this. Substituting this into there, you get box AB minus del A, del B, AA equals 0. I commute these two derivatives and get a Ricci tensor. And then this thing is 0 by virtue of the gauge condition I've picked. So the equation of motion is del AB, box AB minus RBC AC is equal to 0. So this is our version of Maxwell's equations. Now, suppose we were working in flat space-time. Not a general curved space-time. What would this be the solution of the wave equation that represents a plane wave, or indeed any wave with momentum p? We would just simply say, well, the vector potential A is some little a times e to the I theta over h bar. A we could think of as being the product of a polarization vector times the amplitude. Of course, for a plane wave of momentum p, then theta is equal to p dot x. I would like to change one piece of notation here. I'm going to change this to a little a. It's an h bar, yes. So that p is actually the momentum. The momentum of each photon. So you would choose theta to be equal to PA XA. Maxwell's equations would then tell you that p squared is equal to 0. In other words, the thing moves along, in other words, p is a null vector. And the gauge condition tells you that AA times PA is equal to 0. However, we haven't used up all of the gauge degrees of freedom when we have done this, and a convenient further gauge fixing is to make the polarization vector entirely space-like. That you simply do by saying that you can always change A to AA plus dA of lambda, provided box lambda is equal to 0. So you can do that and what that means is that the polarization vector then will point along the direction of the electric field in your wave and perpendicular to P, the spatial part of the momentum. Well, that should be all standard. What happens in a curved space-time? I'm only going to consider frequencies which are large, will give rise to wavelengths which are small on the scale of the curvature. Outside a stellar-sized black hole, that's completely reasonable, because the curvature is governed by scales of the order of kilometers, and light is governed by things of the order of nanometers. So in curved space-time, I want to do things slightly differently. I want to do an expansion in powers of h bar. Of course, we've all seen that before. It's just simply the iconal expansion. So I'm going to write this thing as AA plus h bar BA plus h bar squared CA, etc., times e to the I theta over h bar. It's still the case that the gradient of theta will tell you which way the wave is propagating. Now the trick is just to substitute in to the gauge condition and Maxwell's equations and look at what happens order by order in h bar. That's basically the same thing as doing a high frequency expansion. If you do that, you will get the following two equations. From the gauge condition, del A AA plus h bar del A BA, and then you can keep going, you'll get h bar squared del A CA, but then you'll get an interesting term I del A theta over h bar times AA then I del A theta times BA plus etc. times equals 0. So let's take the first two equations that we get here. Del A theta AA is equal to 0. Since I want to call del A theta PA, always, we can rewrite this as PA AA is equal to 0. That's rather like what we had before. To order 1, we get something more interesting. We get del A of AA plus I del A of theta, which is of course PA, times BA equals. And that determines B for you. Now let's look at Maxwell's equations. Well, those are box minus RAB acting on A is equal to 0. And I think, well, we can just write it out. So this is going to give you a whole lot of terms. Box acting on AA plus H bar box acting on BA, and then that will keep going. Then there'll be an I over H bar del B PB into AA plus H bar BA plus etc. I think that I want my index upstairs. Plus minus 1 over H bar squared PB PB times AA plus H bar BA plus etc. plus 2I over H bar into PB del A, del BAA plus H bar del B BA, etc. And lastly, a term which looks like minus RAB. Got my A's going the wrong way. All times e to the I theta over H bar. So that's a complicated looking thing. Fortunately, we don't need most of it. Let's look at order 1 over H bar squared. That just tells you that PA is equal to 0. In other words, the momentum or the surfaces of constant phase have normals which are null. So it corresponds to a light ray. At order 1 over H bar, you get the following equation. AA del B PB plus 2 PB del B AA plus P squared of BA equals 0. That term is 0 because we already know that P is null. There's something nice that you can do to this equation. let's look at the definition of P. PA is equal to del A of theta. So that tells you that del B of PA is the same thing as del B del A of theta. And of course there's no torsion, so this is the same as del A del B of theta is the same as del A of PB. Since P squared is 0, we know that del B of PA is equal to 0. But this is the same thing as 2PA del B PA, which is the same thing as 2PA del A of PB. And so we see that P, as well as being null, is geodesic. Lastly, let's look again at this equation. We can rewrite this in a slightly different way. PB del B AA equals minus a half AA del B of PB. This basically tells you how the polarization A and the amplitude, the modulus of A, changes as you move around in the space-time. So let's decompose A, the vector AA, into the modulus and its polarization. And see what equations these give for us. So write A is A times epsilon A. This thing is purely space-like because we've chosen the gauge that way. So epsilon 0 is equal to 0. Epsilon I is going to be equal to 1. I'm going to choose it to be a unit space-like vector. Now what does this equation tell us here? If you substitute in, you will get A epsilon A del B PB plus 2 PB del B epsilon A times A plus 2 PB del B of A times epsilon A equals 0. Since epsilon A is equal to 1, you can contract this and you will get, by reasoning we had before, this thing tells you that epsilon A del B epsilon A is equal to 0. And if we look at the equation above and I guess contract it with epsilon, this term will disappear on you. The epsilon will cancel out and you will get A del B PB plus 2 PB del B of A equals 0. So this equation tells you how the amplitude of the wave will change. It's only this equation that we're going to need in what follows. Now let's look at what happens when light propagates in some region of space-time. There is a whole collection of light rays something like that. You can think of these as being along a line of u equals constant, representing something like the retarded time, or something of that kind. I would like to define an affine parameter lambda along these lines, and I want to consider sort of the area of this collection of light rays. So the way to do that is to just take some point in the middle, construct something perpendicular like that, and let's call this vector psi. Psi A is perpendicular to P, which means it's perpendicular to the surfaces of constant phase. Something like that. Then what you do is you ask how this propagates along the light rays. So if you take this light ray and this light ray and move up here, then the way in which psi changes will tell you about how far the light rays have spread apart. So because this is affinely parameterized, I'd like PA to be dxa by d lambda, so that the thing is geodesic and lambda is the appropriate thing, and I know that P will obey the geodesic equation. So this sort of defines an area for you. We don't really need to know any details of this. We just need to know that it is an area. The one thing I know is that as you move up this collection of light rays, energy is conserved. Moving along the right light rays means taking d by d lambda. The area A of this collection of light rays times A squared must be constant. So d by d lambda of A times A squared is equal to 0. Now what we need to do is to use this equation, and it tells us about how the area of the light rays changes. Recall that d by d lambda is the same thing as PA del A. So this really reads PA del A of big A times A squared is equal to 0. This reads PA del A of A times A squared plus A times 2 PA del A of little a equals 0. This term here, however, is the same as this term here. So I can use this to simplify things. PA del A of A times A squared plus 2A, and then it's minus A del B PB equals 0. Now, of course, I can cancel out the A squared from this and get PA del A of A minus 2A del B of PB equals 0. And that tells you how the area changes as you move up and down a particular collection of light rays. Let's apply this to the surface of our black hole. So here we have something which looks like this. So it's evolving a little bit. Lambda corresponds to moving up here according to an time parameter. These are the geodesics which govern the light rays. And we know that the area evolves according to that formula. What I want to do is to calculate the second derivative of the square root of the area. At first thing, that might seem like a perverse thing to do, but it turns out to be rather nice. This is the same thing as PA del A of PB del B times the square root of the area. I can just carry out the differentials here. This is PA del A of a half A to the minus a half PB del B of A. This too is wrong. This 2 should not be here. That's better. Someone should have told me. So this thing, using this equation, is the same thing as PA del A of a half A to the 1/2 del B of PB. Now we just simply carry out the differentiation again. We will get 1/4 A to the minus a half PA del A of A times del B of PB plus 1/2 A to the minus a half, A to the plus a half PA del A del B of PB. But again, using this equation, I can get rid of this term, and I will get 1/4 A to the plus 1/2 del A PA del B PB plus this thing. Well, the way to deal with this is to commute some derivatives. This thing is a half A to the 1/2 PA into R A, B, B, C, P, C, plus del B, del A of PB. So this first term, you can see already, has got some positivity properties. Whatever this is, it's something squared, so it's positive. This term here is a little bit different. This is equal to, gives us a total of something which looks like that. And then lastly, there is plus a half a to the half PA del B del A of PB. Now, we're almost finished here. If this P was inside here, it would vanish as a result of the geodesic equation. So we can put it inside, but we'll have to compensate on something. So we've got a term that we've got to subtract off, namely del B of PA in here. This term is 0 by virtue of the fact that P is geodesic. So we have a final answer for this thing. The second derivative of a to the half is equal to minus a half a to the half RAB PA PB plus, I guess minus, what is usually called sigma squared. Let me rewrite this slightly. Sigma is usually called, sigma squared is basically the square of the shear of these geodesics. We could be very explicit about that. It's equal to 1/2 of del A PB del C PD into GAC GBD minus 1/2 GAB GCD. Given that P is null and geodesic, you can prove fairly straightforwardly that this thing must be positive or 0. This follows from the fact PA being of the form something times 1100 in the appropriate coordinate system, And if you don't believe me, the simple thing to do is just simply to try it, writing it out in excruciating detail. RAB, PA, PB for a null vector is, from the Einstein equations, 8 pi into TAB minus a half GAB times the trace of the energy momentum tensor times PA, PB. This term does not matter because P is null, but TAB, PA, PB is just simply the energy density in the appropriate frame. And the energy density is always positive for any sensible form of matter. That's really only true at the classical level. We will see a counterexample to that. So what have we discovered? We discovered that this thing is negative semi-definite. Not only for this sort of abstract case, but it must be true on the horizon. That's what we have shown here. What is the consequence of that? Well, the consequence is indeed the area theorem. Let's see how that works. Let's suppose that we have a bit of horizon here that is doing something like that, and let's suppose that here dA by d lambda is 0. Now, let's suppose that dA d lambda becomes negative somewhere. What will happen? Well, if you evolve things to the future, you will discover that since this is true, it follows that dA by d lambda is always negative. So what will happen? This thing will shrink down to a point. If it shrunk to a point, that tells you that the energy density there is infinite. That actually is the basis of the Penrose singularity theorem. If I could show you that the energy density being infinite was the same as finding a curvature singularity, I would have proved the singularity theorem, provided dA d lambda was negative somewhere. So in that sense, it's almost a proof of the singularity theorems. However, we believe that black hole event horizons do not evolve into singularities. You'll have to take on trust. It is a usually called the cosmic censorship conjecture, or at least one version of it. There is by now a large volume of evidence which says that that conjecture is true, but on the assumption that it is true, that tells you that dA d lambda can never be negative. Because if it was negative at some point, because d2a to the half d lambda squared is always negative or 0, you can guarantee that a will go to 0 in a finite distance lambda. If that's supposed not to happen, dA d lambda is positive. So I'm afraid that is a rather complicated proof, but it's just the way it is. The original Hawking argument for this was even more complicated, which is why we didn't do it that way. Thus, we can now state the second law of black hole mechanics. The area of the event horizon increases or stays the same. Of course, it is blindingly obvious that this looks awfully like the second law of thermodynamics. So we found the zeroth, first and second laws of black hole mechanics. There is a third law. I'm not going to give a precise statement of the third law. I'm just going to observe that the kappa goes to 0 limit is pathological. The evidence for that is simply that it requires m squared to be equal to a squared plus q squared, and that corresponds to these degenerate horizons where there is no interior region between an inner horizon and an outer horizon. So that's the laws of black hole mechanics. Tomorrow morning we will see that there is more to it. So let's stop there. A question? Pathological because I don't like it. I said that I was going to give a very loose definition of what I meant by the third law. The real point is that when kappa is equal to 0, the whole character of the spacetime is dramatically different. Because it's become this degenerate horizon. You appear to have squeezed out something between the inner and the outer horizons. In the case of Reissner-Nordstrom black holes, you have this internal infinity that is this hugely long tube that goes on forever. For the case of Kerr, was even stranger. So I think that one should just simply take it at face value. There is something dramatically different about it, and it's really odd. Right, so let's stop there then. 9 o'clock tomorrow.